Continuity. Okay, this should be pretty straightforward. And I know I said that yesterday, and I underestimated how much we review. We had to do advanced functions. That was my fault. But this is new, except I think pretty straightforward. I think everything I say, we're going to get a lot of nods like, yeah, of course that would be true. Of course that has to be true. You know? And I trimmed up the homework, but I didn't have to trim it up that much because a lot of the questions are really fast. Like boom, boom. You know what I'm talking about? Some homework's like every question's like, ugh. And then some questions like, as fast as you're reading them, you're writing the answers. I think that's true here. Continuity. In basic terms, a continuous function is a function that has a graph without any gaps or breaks, has a graph that can be drawn without lifting the pencil. Either of those two things can be true. You can think of it either way, and that's what a continuous function is. So for instance, this function is continuous because I put my pencil down at one end. I start here, and I just go, whoops, hey, stop that. I start here, and I just go. And continuous functions are like that. They're all one piece, if you want, even though we shouldn't use that word because that starts to lean towards piecewise, and I don't want to fall into that stuff. But it's all one section, you know, all connected, continuous. And there are many types of discontinuities that come up and that we've ran into. I just need to warn you, your textbook has a slightly different understanding of continuity than this. Might affect your homework answers a little bit, but it's certainly not going to affect the test. I knew about the problems in the textbook before I wrote the test, and I went, stay out of the textbook problems. It's one of those interpretation things, and I'll explain it in just a minute. So for now, I'm going to explain it how most people understand it and how most math textbooks handle it, and then I'll explain the little difference in your textbook. And it won't affect you on the test, I promise, because I was careful. Here's the discontinuities we've mentioned so far. Holes. A hole means this function goes for a while, then stops. You have to lift your pencil and go over here and draw it like that. I think there's a nice little... yeah, here we go. Watch the pencil. Whoop. What we're saying is there's a gap there. I know we put a little circle there, but the circle isn't part of the graph. The circle is just like, everybody, look, 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 look. It's a hole. Yeah. We call that point discontinuity. Then there's these, jump discontinuity. Because of piecewise, I think you ran into jump discontinuities before where it's like, oh, one definition over here and then another definition over here. Here's you drawing it with your pencil. You just go, woo, and then you jump up to here. So you have to lift your pencil. It really is that simple. Discontinuous if you have to lift your pencil. And then finally, vertical asymptotes. Yes, you go straight up like this, gone. And then you have to lift your pencil. Sorry, it's jumping ahead on me. Up we go. And then you do the other side. Okay, here's the little thing your textbook changes about all this, and I think they're wrong to do it, but this is what they say. They say, this one's a discontinuity, yes, because it jumps within its domain. But they don't count these ones as discontinuities because they say it can't be a discontinuity if it's not in the domain. See, this is a domain problem. It's not a discontinuity, and I think that's weird. So they use this phrase. They love this phrase. They say this thing is continuous on its domain. Yes, there's a domain issue, but if you just stick to the domain, it's continuous. And the same here. If you just stick to the domain, it's continuous. These have domain issues, not continuity issues. They separate the two. Most textbooks don't do that. They say continuity problem, continuity problem. Okay? So continuity of point. A function is continuous. These following things have to be true. The function has to be defined. Of course it does to be continuous. It has to be defined. There has to be a value there, and the limit has to exist and head there. And that's what I mentioned during the limit lesson. If a function is going to be continuous at a point, it has to exist there, and it has to be heading towards there. That's simple. It seems like too easy, where it's like, you came all this way to tell us to not lift my pencil. My pencil's got to come to the same spot from both sides, and there's got to be something there. Yeah, that's all there is to continuity, actually. Otherwise, we call it discontinuous. Test the following functions for continuity very quickly, because you have seen these. Polynomials, always continuous. You never have to worry about them being discontinuous, so it's certainly continuous at x equals 2. This one, discontinuous at x equals 2, and this is the only real point I have to make on this whole slide. My question is this a vertical asymptote? It certainly looks like it. Or is it a hole? How do you decide if it's a vertical asymptote or if it's a hole? Yeah, if you factor this and it cancels, then it's actually a hole, not a vertical asymptote. It can fool you that it's a vertical asymptote, because it really looks like one. This particular one does factor and cancel, so it's a hole. Mr. Lynch, how are you? Great.
I think we figured out our recording puzzle.
Are we 0, 15, or 100?
We're 100. So you can come and see me at some point today and I'll explain it.
You're my hero. Made my day. Yeah?
Got you there.
There's an adult who's got it together. I came to him with a problem yesterday and I said, I need this solved. I can't have the 0 solution. I can't have the 15 solution. I need the 100% solution. This has got to get fixed. Comes back today, fixed. Okay? No problem. No stress. All right. Okay, let's just break down this whole thing a little bit, though, because I don't want you to be confused about the whole situation. And this was supposed to be beat to death in advanced functions, but maybe it wasn't. At first glance, looks like a vertical asymptote. Looks like x can't equal 2. But if you go a little farther, what you find is, if you factor this, that cancels. So weirdly, this function of x squared minus x minus 2 over x minus 2 is a line. G at x is x plus 1. And you're like, well, what's all this nonsense about? All that's going on here, this cancellation here, it means, watch, I'm going to do the whole thing right here. There's a hole there. That's all that's going on. Okay? So when you cancel that thing, it's all this work. Factor, cancel. You know, you had to state the restrictions. You had to go, was it a vertical asymptote? Was it a hole? You had to do all this work. Graphically, all that's happening is, oh, it's a hole. Where's the hole? It's at 3. The limit tells you where the hole is, at 2, 3. So you can actually fix the hole, if you wanted to. Seems like such a weird exercise. So you got a function that someone created that has a hole in it, and my job is to fix the hole? Let me just tell you a side story that sort of relates. I went up to my pool. It's all pool stories today. And my pool, the pump runs for 8 hours a day. And it always runs, I always run it, between 5 in the afternoon and 1 in the morning. So I went walking out in the evening to do something, I forget what I was doing, and all of a sudden I went walking out and I just stopped and I was like, something's wrong. Because the pump wasn't running. I went down and the whole switch mechanism was melted out of it because it had shorted out. There was an electricity problem. There was this electrical moment it had, and I had to take the whole thing out and the contacts were all melted. I had to get a new one, rewire it, replace it, the whole thing. Why did I tell you this story? This has electrical applications. Electricity every once in a while does funny things. It does things other things don't do. It turns off. It can go not to infinity, but the voltage can go like this and the breakers can go. So this has very big electrical applications. That what we're talking about here. When there's holes in things, things go wrong, and can we fix the hole so that my pump doesn't short out every time there's a lightning storm, or every time there's a surge in the line. If we define the point h at 2 equals 3, we can fix the hole. We can go back to this function and say, oh, instead of it being a hole at 2, 3, I can actually put a point at 2, 3, and now it's not continuous anymore. So it would be continuous at x equals 2. This one's vertical asymptote. And this one's the jump discontinuity. If you sub in 2 into here, you get 0. If you sub 2 into here, you get 3. I think you've seen those piecewise ones before, where they approach different things from either side. There's some great homework questions on this. Yeah, it's a great homework list. I say great in that it's the right stuff. It's asking the right questions for what I need you to know for the test and for next chapter. So a little more about removing a discontinuity. It says create an extended version of this so that it has no discontinuity. You've got to do that in a separate sheet of paper. A little more complicated one than the one I just did. Ooh, I missed that. Was it just a 7? Yes, it was. Okay. Create an extended version of the function x cubed minus 7x minus 6 over x minus 3 that has no discontinuity. Okay, forget the rest of the question for a minute. I'll come back to the rest of the question, but just imagine you ran into this thing and you didn't know what was going on with this whole thing. Whether it had a discontinuity, whether it didn't, whether it was vertical asymptote, whether it was whole. Here's the whole thing, the whole story. Little pun there for you on a Thursday. Here's the whole story. X minus 3 in the denominator, way back in grade 11, is a problem. We have a restriction. X can't equal 3. Our question for today is it a vertical asymptote? It looks like one. Or is it a whole? To be able to find out, we have to factor the numerator. And so now we're reaching back into advanced functions to see if you can factor. Let x, actually I'll use the notation we did in advanced functions. Let p at x equal x cubed minus 7x minus 6. Now in advanced functions, then you would have gone p at 1, p at negative 1, p at 2, p at negative 2, p at 3, p at negative 3, and you just would have kept going and hope you find a number that makes this come out to, what has it got to come out to? 0. Yeah? That's what I'm really looking for. And if that's like, oh, I didn't know it was 0, just hang on. I'm going to redo the whole procedure here so you can really see it. However, there's a smart value to try here to check if this is a whole. I don't really care about 1, negative 1, 2, negative 2. Those are all very interesting, and they might help me factor. But there might be a better place to start to really get to the bottom of this thing. He likes 3. And if you get to one of these and you're like, okay, I did 1, negative 1, 2, it'll work. But 3 is what we really care about here, so why not start there? Yeah? So p at 3 equals 3 cubed minus 7 times 3 minus 6. I get 0. And apparently that makes us happy. If you've forgotten why that makes us happy, you'll see in a second. But apparently that makes us very happy. Because our conclusion from that is, therefore, x minus 3 as a factor. And that is not nearly as dramatic as it seems. It's given fancy names, factor theorem, remainder theorem, and so on. But all we did was sub it in and say 3 makes this thing 0. Then I know x minus 3 is a factor in this thing somewhere. And you could do long division, which I know you love, to divide this thing out. But there was a faster way. Yes, synthetic division. Here we go. Here's synthetic division review. 1x cubed, 0x squared, negative 7x minus 6. My magic k value is 3. And if this is completely lost, like you're like, I have no idea what you're doing now, you're stuck with long division probably. You probably want to relearn synthetic division to be able to do these. And then it's just a little dance like this. Add and multiply. Oh yeah. 0. Huh? So what I get here is p at x is the x minus 3 and then an x squared plus 3x plus 2. So, all the way back to here. And I asked the important question. What kind of discontinuity is x equals 3? It's a whole, how do we know? Yeah, if this cancels out, it's still a it's still a domain issue, but in some ways it's not as bad a domain issue. So I've got a hole in this function. There's a hole at three comma. How do I find out where the hole is? Yeah, plug it into this remainder that we got here. If you want, what you're doing is going, find the limit as x approaches. Sorry, I'm addicted to infinities here today. Find the limit as x approaches 3 of this function, which is limit as x approaches 3 of this x squared plus 3x plus 2. And what I get is 9, 18, 20. 9, 18, 20. And now find that I can do what they wanted, which was to fix the hole. Here's how I fix the hole. I make a piecewise function. I go, okay, this function is normally x cubed minus 7x minus 6 over x minus 3. But I'm only going to let that be the definition when x is not equal to 3. When x is equal to 3, I'm going to make the function value 20, because that's the exact point, it's the exact dot I need to fill the hole. Here's a quick little sketch of what's going on in this thing. There's some kind of parabola that's got a hole in it. And so what I did was fix the hole by putting a point at 3 comma 20. Seems like an exercise in futility, but it's not. You know, we want to know where these holes are, we want to know where the discontinuities are, and we want to know what's it going to take to fill them in. Yeah, it's I know what it feels like. It feels like, so you're just sort of putting something back in the hole? And the answer is yes. And just imagine an electrical application where you go, every time this happens, every time these switches are flipped and this comes on, all at this time, boom, we have a short. So we need to stick something in that hole. We need to go, boom. We need something to happen at that moment to make sure that we fix that. That's not a perfect analogy, but it gives you a feel for where would this even come up? Why would we even care? Question. That was my extended version of the function that had no discontinuity. This thing has a discontinuity. Well, so what I did was I said, use this rule, unless x equals 3. If x equals 3, don't use that rule. Use my other rule, and then you'll get a function that doesn't have a hole in it because you didn't use the rule where there was a hole. And that's what piecewise is for, essentially. You just go, no, let's change the rule over here. Let's change what's going on for this section. There's the answer right there to the question. There's the extended version of the function where I added on to my definition of the function to fix the hole. Can we always do that? No. You can't fix something that's got a vertical asymptote. There's no way to fix that. But I can fix a hole because I can just put a dot in it. That simply. Questions here? Yeah. Find out where the limit was heading towards. So I was saying, okay, that's fine. I can't sub 3 into this because I get undefined. But I can sub 3 into this, which tells me where the hole is. I can find the limit. Even though I can't sub in the value and find out what the value of the function is there, I can find out what it's heading towards and find out what point I wish I had there. Continuity at an endpoint. A function f at x is continuous at a left endpoint or is continuous at a right endpoint b of its domain if the limit approaches that value. So we still do say that these endpoints are continuous even though you can't come at it from both sides. I think that's obvious, is that we really couldn't call this endpoint discontinuous. Maybe there's some limits that don't exist there, but we wouldn't go so far to say as this doesn't hook up with the rest of the function. It is continuous there. I make that point. I just dropped that in there. Like we don't use that very often. And an important note about your textbook, they think of it as if you've got a continuity error, if you've got a continuity problem, that's also a domain error, then they say, well, it's not a continuity error. It's a domain problem. You know what I mean? So that they make that distinction. So when you're doing homework, just be aware of that. They think 1 over x is continuous on its domain. Because they go, well, yes, it's continuous everywhere. And you say, well, what about x equals 0? Well, that's not in the domain, so we don't care about that. And that's the approach they take. Okay? It comes up very rarely in the homework, and I carefully avoided this issue on the test. I went, I just won't ask questions that put you into that distinction.